Okay, so first we will recall what we have done last time. Last time we showed that if we have a circle, then the circumference of the circle is LR is given by 2 pi r. And we showed that the area of the disk so both of this we started with the assumption that the ratio then we check that these two constants are actually the same. This will be the pi. So we didn't justify the choice of this assumption. Why is this ratio constant? Why is the ratio constant? Let's consider a diameter. Now, if we enlarge the circle, if we double the radius, we can see the circle becomes twice as big. So the circumference will become twice as big, and the diameter will also be twice of the diameter. In this, we can see they grow at the same rate, so the ratio is constant. We can show this if we enlarge or if we shrink the circle, ratio is constant. For the area, why this ratio is constant? We can consider a square inscribed square. Not a very good square. Let's need to call this. Okay. So what's the area of this square? Area, what do you see? The area of this square. To find the area, we need to find the size of this edge. What's the size? If we know this is R, radius is R, what's this side?
The size is basically square root of r plus r, basically.
Okay, yes, so the square of this, square root of the square. Then we see the area of the square. Okay. Then the reason for this is constant is the ratio of the disk to the area of the square. This is constant. For example, if we double the radius, the circle, the disk, and the square, they grow in proportion. So the reason for this is this area of the disk, area of the square is constant. So therefore, we justify the assumption that this ratio is constant. And then we use the increment argument. We checked the two constants are the same. So here the argument, increment argument. Okay, then we move to angles. So two angles, we say they are congruent. Congruent. If they equal, you have the same measure. So two angles, they may happen at different location. If we can move one to the other with overlapping edges, then they have the same measure. We see the two angles, they are congruent. So we use this notation, alpha equals beta. Even though they may be two different angles, if they're the same in measure, then we say they are congruent. It's the same as they are equal, but here we just want to emphasize maybe there are two different angles. Yes, Kira.
Isn't the symbol for congruent with like equal sign with a line over it or something? Are we supposed to use that or is just an equal sign?
So if we have the triangles, okay, so later we have more relationship between this. Is this what you're talking about, Kira? Okay. So here, we could write well, I prefer this because this tells us the two angles have the same measure. So they both works. It depends on what you prefer. Okay. And the last time we also introduced this supplementary angles. So two angles, the supplementary if the summation. last time I made the confusion of this notation as a complementary. This is for a different thing. Two angles, they are complementary if the summation 90 degree. So for different terms. Now we consider the intersection of two lines. They intersect at one point, we call this O. First line, we see this A, B. Second line called C and D. This opposite angles, we use this AOC, BOD for the two opposite angles. Sometimes we also call this the vertical angles. So here, this vertical is from the word vertex. It means these two angles, they share the same vertex O. Okay. So opposite angles or vertical angles. And then we showed that the vertical angles, they are the same. Okay. And we'll also consider two lines. And a third line that intersect both. We will call this third line transversal. A line that cross both lines, we call it a transversal. Now we can label the angles. The order doesn't matter, it's just how we order this. Too many angles, I will use the numbers. Okay. Adjust this. There's some terms for the relative position of these angles. For example, this angle 1 and angle 5. They are angles at different vertices. Moreover, they're on the same side of the transversal. And the third condition is one is in the interior and one is in the exterior.
Excuse me.
Yes.
I can't read the number one.
The
At different, I can't read the other word.
you mean the last word?
Yeah. Oh, vertices. Okay, got it.
So yes, so it's the plural form of the vertices. Yes, very good. Whenever you see something not clear, you can let me know. I will rewrite it. Okay, we call angle pairs with such relationships. We call it a corresponding angle. We call it a pair. Okay, yes, Kira.
How do you tell if an angle is interior or exterior?
So it's relative to the, we'll have two lines. This common domain, we call it the interior. So the rest, the exterior. With this, so this will be these four are the interior angles, and these four are the exterior angles. That makes sense?
Okay, got it.
Okay, okay. Okay, Kira, you asked. Now, could you give me a second pair of corresponding angles? We have one pair, 1 and 5.
3 and 7.
3 and 7 is on the same side of the transversal at different vertices, and one interior, one exterior. Now we see 3 and 7. Amy, give me another pair.
6 and 2.
6 and 2. So angle 6, angle 2, so at the different vertices on the same side of the transversal. One interior, one exterior. Jessica, another pair.
4 and 8.
4 and 8. Okay. Angle 4, angle 8. So these are the 4 pairs of corresponding angles. Another notation for this is the alternate angles. They're also at different vertices. But they're on the different side of the transversal. And both interior or exterior. alternate angles. Aaron, if we check the graph, could you give me a pair of alternate angles?
Let's see now. 6 and 7? Oh no,
So
actually,
let's
no.
check.
6 and 3, 6 and 3, 6 and 3.
6 and 3. 6 and 3, we can see are they on the different sides of the transversal?
Okay, no, 6 and 4.
6 and 4. Okay, now let's check. 6 and 4, different vertices, different sides of the transversal, and both exterior. Okay, that's our one pair. Fred, can you hear us, Fred? Okay, let's turn on the camera if you can. Give me another pair of alternate angles.
8.
2 and 8, okay. Second pair, 2 and 8. So 2 and 8, different vertices, different sides, both interior. Sophie, can you hear me, Sophie? Let's see. Kira, another pair of alternate angles.
4 and 5?
4 and 5.
No way, that doesn't work.
Uh-huh.
5 and 3.
5 and 3. 5 and 3. Can see different vertices, different sides, both exterior. That's Peter. Okay, Peter, can you hear me, Peter? Maybe not. I will check with him later. Okay, so the last pair will be, let's see, with 1 and 7. There are some further distinctions between the 4 pairs. For corresponding angle, one interior, one exterior. But this, both exterior, 3 and 5, these 2 pairs called alternate exterior pair angles, alternate interior angles. Okay, exterior, so it's 3 and 5. Exterior, 4 and 6. 1 and 7 and 8. Okay, some relative positions of the angles. The useful application of this is when two angles of this pair are the same. For example, if these two angles are the same, we know the two lines are parallel. Okay. A similar theorem is we can replace the corresponding by alternate. The same thing if I alternate. Okay. And the reason why they are equivalent, corresponding and alternate, is the previous theorem. The two vertical angles, they are the same. So previously we proved okay. We have mentioned this term proof many times. Or proof. And we have encountered this in the previous algebra course in our homeworks. So next we'll talk about mathematical proofs. Okay. There are 4 different types of proofs. The first one, the most basic one, is direct proofs. A typical example that with direct proofs is the thing we had in our homework. Okay, so to prove this one, we have the direct proof. So where do we start our thought process? So this is the same as we multiply both sides by 2. Okay. So this is if we subtract this from both 2ab from both sides. Then we recognize the right-hand side is the complete square. For any pair of real numbers, a and b, the difference is again a real number. The square of a real number is non-negative. We know this is true for all pair of real numbers. Since they are equivalent, this is true for all real numbers. That means a and b are real numbers. Aaron, did I introduce this before?
I've seen it before, but you didn't introduce it.
Okay. So what does it mean?
I sort of forgot. It's sort of like I forget because this was like 2 years ago. So, but it's sort of
Okay.
confusing and sort of means position in our thing.
Okay. So normally when we say an element in a set, so this will be a set. This is one element in the set. So what is the set? Is a collection of elements. This is one element in the collection. So X in A. Now we use this for all real numbers. So A and B in the set of real numbers, it means A and B, they are real numbers. Okay. So this is a direct proof. Let's just prove another thing. Property. We consider two non-negative numbers. Then we have okay, let's think about it. How would you prove this? It's not difficult, just some practice of proofs. Aaron, what would you do?
What?
How do you prove this? Why the square of x is less than or equal to the square of y?
Cause x is greater than 0 but less than y.
Okay. So a few steps we can fill in the gap. So because they are non-negative, if we multiply both sides by y, let's see, 2 steps. We multiply all of them by x. X squared x1. Because x is non-negative, it does not change the direction of inequality. We still have this inequality. Then we multiply both sides by y. Again, because y is non-negative, the multiplication of both sides by y does not change the direction of inequality. Now we use the transitive property of the inequalities. This less than or equal to xy, xy less than or equal to y squared. Put them together. We get x squared this completes the proof. There are different ways to prove this. Okay, let's find a different way to prove it. We want to prove this is less than y squared. We can subtract x squared from both sides. Then it's the same as second proof. Okay, now let's recall the formula for the difference of two squares. Jessica, you remember this formula? Amy, we can factorize it in something.
X, y squared minus 2, wait,
Factorization, how do we factorize this?
Can turn it to I don't know.
Okay. That's fine. Just check. Okay, think about this. And then Kira, what about you? Do you know how to factor out this?
Not really.
Okay, Aaron. The difference of two squares.
And
Okay, so
wait, what? Oh, y times y minus x times x.
if I give you the result, you will say, "Oh, it's so easy." Okay,
Wait, no,
I'm
y
sure.
y minus x times y minus x.
Y minus x and the y plus x.
You should have told us that earlier.
Okay. Maybe I tricked you, but it's not difficult, right? Amy, what do you say?
Yeah.
Okay.
Isn't that supposed to be y squared minus 2xy minus x squared?
Well, okay, now I have some question. What
I'm
to
like,
use?
if that y were a y plus x, then wouldn't that be the case? If that y minus x were the y plus x.
Okay, so after class, you should verify this. Okay, now we want to check whether this is non-negative. The product of the two. The first, what can we say about this one? Under this condition. So two numbers, they're both non-negative, so the summation will be non-negative. And because x is less than or equal to y, the difference will be non-negative. Now the product of two non-negative numbers is also non-negative. That's how we prove this relation, and which is equivalent to what we want. Second proof. Okay, you may be able to find a third or fourth proof. A proof of this type is a direct proof. Direct proofs. Okay. The second type is proof by contraposition. So what is a contraposition? What does this mean? This is a term from logic. Okay, something is logic, something is not logic. So is that a logic? Okay, basically it means if two statement A oops, this. Then the contraposition is not B. not A. This is the contraposition. Okay, so think about this, and during the break, we will have some examples of the contraposition after the break. So we will resume at 8:19, so 5 minutes break. Okay, so what are this? What does this mean? For example, statement A, it rains. It's raining. Statement B. The road is wet. Okay. So our proposition is A implies B. It's raining. Okay, now we will construct the contraposition. Contraposition starts with not A. It's not raining. Then not B. Okay, let's check. Kira, what do you say about the statement not B? If this is B, it's not B.
Then not B would be the road is not wet.
Okay, very nice. So the road is not wet. Then the contraposition. Not B imply not A. So in our case, it means if okay, now let's compare the two propositions. A imply B and not B imply not A. These are two statements. I claim they are the equivalent. If this is true, this is also true. If it's raining, the road is wet. If it's not wet, it's not raining. Okay. Sometimes we want to prove this one, maybe not that easy, but we can start with the contraposition. If we can check this, then we also have the proposition. Okay, let's see a mathematical example, a daily life example, mathematical example. Very simple one that has some practice. Okay, so we verified. So let's take this for granted, and we know this is correct. Now our proposition. Okay, so we want to check that this is not a real number. We want to use the property over there. To use this, we will start the contraposition, the opposite. Okay, Aaron, this is the statement A, then what's not A?
I mean, I is a real number. That's
Okay, okay, yes. So this is a statement A. The not A is if this is a real number, then I square, according to our theorem, should be non-negative. However, we know that I square is actually -1, which is less than 0. So this violates the theorem. It does not. Okay, Aaron, we heard that. Okay, it's Kira.
What's the difference between this one and like proof by contradiction? Because right now it seems like they're sort of similar.
Okay, it's very similar. So the difference is this the logic. So let's say proof by contradiction. So that let me see. Okay, so the way I stated over here is more like the contradiction. I see why it's the confusing. Yeah, I agree with you. This is more like the contradiction. Okay, I will think about this. I will think about this. Let's give the proof by contradiction and see the difference. It's a very good point. By contradiction. So contradiction means something that's inconsistent. A typical example is what we had in our algebra course. Let's recall the theorem. Amy, do you remember this theorem?
Well, I know the square root of 2 is rational, but
Okay, so how did we verify this? Jessica, do you remember this? Okay. The Kira? Aaron, what about you?
We verified that because square root 2 equals something 1.41 or something like that.
Okay. So that's the numerical result. You can find the exact value or something. Okay, Kira.
If we're doing proof by contradiction, then we could do like square root of 2 is rational and then prove that wrong to make.
Okay. So now let's start. So proof by contradiction.
You already wrote that down once.
What's that?
You already
Aaron?
wrote that down.
Okay. It's up to you. Okay. We suppose the contrary. And we will derive a contradiction from this. So it's a rational number. It means we can write this as the quotient of two integers. Also, we can assume these two numbers are co-prime because they have their common factors. We can always simplify it. Okay. Then we take the square of both sides. We multiply both sides by q squared. From here, we conclude this t squared is 2 times integer, it must be even. the product of a number with itself is even, it means the number itself must be even. Otherwise, the product square of an odd number is still odd. This is a key step. P must be even. So here, if P is odd, then P square will also be odd. Since P is even, so P can be written as 2m for some integer. Now we use this updated information in our formula. Then the power rule, this gives us 4m squared. We can simplify this, we get from here we conclude this in the same argument, so q squared is even in the same argument as we have done before, q is even. So q will be 2n. Okay. Now we have a contradiction. So P is 2m, Q is 2n. Both numbers are even numbers. They cannot be co-prime. We have 1 here. 2, 3. This contradicts. Yes, Kira.
I sort of forget what's the different. Sorry, what's the definition of coprime again?
Okay, co-prime, it means their common, the greatest common divisor. Greatest common divisor. You remember this? So two numbers, for example, this one, so 12 is 6 times 2, 18, 6 times 3, so this will be 6. Greatest common divisor. So two numbers, they are co-prime. If their greatest common divisor is 1. However, for two even numbers, that means 2 divide P, 2 divide Q, so the greatest common divisor is not 1. Correct. Does this refresh your memory? Okay. And Amy, is this how you proved the theorem? Okay, it's a very standard approach. So we assume something, we assume the opposite, and from there we derive a contradiction. Okay, another theorem that we use this proof by contradiction is Euclidean theorem. There are infinitely many prime numbers. Okay, so the proof by contradiction. If there are only finite many, suppose there are only finite prime numbers, we can list all of them. Since they're all finite, list all of them. Okay, P1, P2. We don't know how many, but only finitely many. Okay. So this means these are the only prime numbers. Okay, now let's consider another number. This number could be very large. Okay. Since we assumed these are the only prime numbers, this number has a prime factors. Okay, let's think about this question. It's not easy to answer directly, but let's check one by one. Okay, I will start with Aaron. For this number, is P1 a factor of this number? How do we decide this?
Well, P1 times something times something times something equals n, so therefore P1 should be a factor of n.
What about this one?
Well, a 1 plus, yes.
So what's the remainder if we
The remain
modular? N mod P. So this number has two parts. What's the remainder for this one if we divide by P1?
P2 times something 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 to Pn, I guess.
So that's the quotient. What's the remainder?
One.
Okay, so eventually, so this part is divisible by P1 because it has a factor over there. So only one left. This is 1. It implies P1 is not a factor. Okay, Kira, what about the P2? Is the P2 a factor of n?
I don't think so,
And
because
why?
if it's there's still a 1 as a remainder.
Okay,
Outside of
right.
it. Even if you divide the rest of it by P2, then it would not have a remainder, but then there's a 1 in front of it.
Right.
That's not
Okay. So this part is divisible by P2. So again, we have a remainder over there. And mod P2. Also 1. The answer is no. Okay, Amy, what do you say about P3? Is P3 a factor of this number?
I don't think so.
Okay, what's the argument? So here, I skipped a few terms. This should be P3, P4, all of them. So I skipped a few. If we want it will be P3, P4, P5, every one of them. Okay, we want to check if P3 is a factor of n. So we check what's the remainder. Find the remainder when divided by P3. This part, 0 remainder. The remainder will be 1. Again, is 1. So P3 is not a factor. Okay. So then using this argument, we can check them one by one, and we conclude none of them is a factor of n. Okay, now something strange. Our assumption is these are the only possible prime numbers, but none of them can divide n. So even this number is not a prime, the prime factors of n will not be any of this. Okay, so we assume that this is everything, but somehow we got something else outside of this list. This is a contradiction. So none of the, okay. So now we get a contradiction. In the beginning, we assumed these are the only prime numbers. However, this construction forces us to admit the existence of other prime factors because none of them works for this number. There must be something else. This is everything. We find something else, then this is a contradiction. Okay, so let's go over the proof. We wanted to show that there are infinitely many. The method proved by contradiction. Suppose there are only finitely many. There are only finitely many, we can list all of them. It means this exhausts the list of prime numbers, nothing else. We have this finite list, we can construct a new number. The product of all of them add 1. For this new number, P1 is not a factor. P2 is not a factor. And any one of this is not a factor. This one, it must have some factor because it's a very large number. That factor is beyond this list, so we can get something else. This is the contradiction. Okay, Aaron, does this make sense? The logic?
Yeah.
So why do we have a contradiction?
Because the person stated that there are infinitely many prime numbers. But Euclid's theorem says there are infinitely many prime numbers.
Well, that's not what we are arguing.
Oh, I mean, you listed all of them, yes.
Yeah. So we list all of them, then we find something else. So this is not all of them. Okay, Kira.
Is there any proof that there is a prime number that fits the factor of n? Or is it just like theoretically there's another one?
So the point here is initially we claim, okay, we have finitely many and we found all of them, there's nothing else. So this is the claim. This is the list of prime numbers. Everything outside of it is not prime. We have include all possible prime numbers over there. Okay, so this is the assumption. However, based on this assumption, we found something else outside of this list. Now we have to admit this is not all of them. We start with the assumption this is all of them. We end with the fact it's not all of them. That's the contradiction. It's like with some, I'm not sure if it's a good story. We get robbed by someone. They say, "Give me all your money." Okay, you give him all your money, but then they find something else on the pocket. So that's the contradiction. It's the same thing here. I say, give me all your prime numbers. But in the end, we found some prime number in our pocket. That's a contradiction. It's very important with this assumption. Give me all your prime numbers. If that's all, what is this in our pocket? That's the contradiction. Amy, does this make sense? What do you think?
It's a bit hard to wrap my head around.
Okay. So this process may be not that easy. You can try a few cases. Suppose if there are only 4 prime numbers. So okay, it's very extreme. Not always the case. If there are only 4, we have 2, 3, 5, 7. Now we construct the number 1 plus 2, 3, 5, 7. This one is a large number. It has some prime factors. P cannot be 2, because if we divide this by 2, can remain the 1. The same way, P cannot be 3. P cannot be 5. P cannot be 7. So this new number, it has some prime factor beyond this list. We can always find something else. Okay, so this is the proof by contradiction. And the last one is mathematical induction. And we will learn more about this next time. And we will learn only the standard one, mathematical induction. In the future, you will learn more variants of this. You will learn some like a strong induction. But we will focus on this one first. Okay, so we'll stop here. Any questions about today's lecture? Okay.
What's the